All right, day 3 and the last day of the Hardy-Weinberg Equilibrium Modeling Lab, we are going to do a chi-squared analysis. So everybody's favorite about writing a short conclusion after you do some calculations on a set of data compared to another expected or observed set of data. That being said, being able to do this is completely not dependent on whether or not you finish day 2. So there's not an excuse really to not finish this part, even if you didn't pull your 10 generations of your large and small populations. However, you do need to have at least one population pulled for the F1 generation of both the large and the small. So for this chi-square analysis, we're going to be using the P generation allele frequencies, which is the ones that we decided to determine if the F1 generation is in Hardy-Weinberg equilibrium or not. And yes, we could look at conditions, but because we're modeling it, we're the ones who chose the conditions. So based on the conditions that we chose, we want to see basically the difference between the small population and the large population. If there's any discrepancy in being able to be like, yes, it's in Hardy-Weinberg equilibrium, or no, it's not in Hardy-Weinberg equilibrium. And the only caveat is, remember that when we write a null hypothesis, we can only reject or fail to reject. So we can't say it is or is not in Hardy-Weinberg equilibrium. We can only say that it is, that our data currently shows that we can support our null hypothesis or we can't support our null hypothesis. And so you'll see what the null hypothesis says soon when we get to it. So we're going to compare our observed AA, AB, and BB genotype data for our F1. Remember, we pulled it at the very bottom of the tables. And what we mainly focused on when we did day 1 and day 2 was the P and Q values, which were the allelic frequencies. But we're actually going to focus on the genotype frequencies now, because that's what we would actually be observing in a population. So we're going to be comparing with what is predicted by, if you just did straight mathematical calculations without taking into consideration anything, you'll be using your parental P and Q and calculating out what would be the AA genotypic ratio, will be the 2PQ genotypic ratio, and the Q squared genotypic ratio. And so it's a kind of cool way to have a rigid thing we're comparing to instead of being a little bit wishy-washy sometimes on what the expected values are. So you will do it guided in this video for the small population with me, but you are going to do your own chi-squared analysis showing all work and all setup and all calculations in your large population set of data that you're using. You're still using the same P value, P and Q values from the parental generation in the allele frequencies, but your F1 generation genotypic ratios and numbers should be different from anybody else's, because we're all using randomization functions. So no two people should really have the same numbers unless just by chance. We're going to be using the spreadsheet to do the math, because Excel and Google Sheets are actually just giant calculators. They're a little less wieldy. They're a little more unwieldy than like a graphic calculator, but they do the same things on them. So we'll be using them to do our math for us. So we don't have to use a calculator, use our phones, or use our heads, because that's tiring. And just as a remembrance, the chi-squared value is, the chi-squared formula is the sum of when you do the expected minus the observed minus the expected squared divided by the expected. And that's for however many groups you have. So if you're doing 5 groups, you have to do this 1, 2, 3, 4, 5, 10, and you have to add them all together. And that would be your chi-squared value. So our null hypothesis, again, always the emphasis is on no significant difference. So we're comparing, like over here it says, we're comparing our actual data, our observed data, to our predicted data or expected data based on this calculation. So the null that I wrote, that you don't have to write exactly, because you might be comparing it with slightly different language and you want to write it in your own format, because if you're just copying what I write, a lot of times you're going to forget how to do it when you actually have a test. So what I wrote is, there is no significant difference between the number of individuals observed in the F1 generation of genotypes AA, AB, and BB compared to the number of individuals predicted using the Hardy-Weinberg equilibrium equation, P squared plus 2PQ plus Q squared equals 1. And so again, we're comparing the number of individuals. Notice I said number of individuals, which means that I'm going to be working with individuals here, and we're not working with the allelic frequencies. We're not working with the genotypic frequencies. We're actually going to be working with number of individuals, which means if I do this calculation with P squared, 2PQ, and Q squared, I have to make sure that I multiply by the population size at the end in order to get the actual number of individuals instead of just getting a proportion of the individuals, because then I can't actually compare them. Remember our data sets, we actually pulled number of individuals, so that's already easy on the observed side. We just have to make sure that we account for on the expected data side too, in order to make sure that, our chi-square comparison is a valid comparison. And even before going into doing the actual chi-square comparison and doing the actual chi-square calculations, you already know that we are doing AA, AB, and BB. So we have 3 groups, which means n equals 3. Therefore, degrees of freedom is n minus 1. 3 minus 1 equals 2. And we're using a p-value of 0.05 as always. And so our critical value that we will be comparing our end result of chi-square calculation value to will be 5.99 as pulled by the chi-square data table for AP Bio. And you can look it up. You can go back to our reference from a long time ago, or you can just Google the chi-squared form and it should pop up. And you should be able to use a 0.05 and a degrees of freedom of 2 to find a 5.99. Okie dokie. So let's go to our Excel spreadsheet or our Google Sheets spreadsheet. Now, the parental generation allelic frequencies are what we're working with. So we're actually pulling these ones, and these ones are the ones that we actually got to pick. Remember, we picked a number and then we picked 1 minus that number as the Q. And so just to make it easy and keep all of our references in the same page, we're going to just, copy it down here. And so in order to do that, we're going to label parental, and we're going to want to, write the equals and then go click on that box, copy that data down and bring it down to here for us so that we don't have to continue scrolling up and down because we're lazy. And we have the ability to be lazy because we worked hard earlier. So we're just copying those data down, and let's do our p squared, 2pq, and q squared right here. So the easiest way to do this, because we know that p squared is just squaring the value of this p, and the p is 0.24. You're going to equals, and then you're going to take your value. Right? You're going to click on your value to get the value from that cell. And you have to do the up caret actually, because unlike the calculators, we don't have a square function with a pretty screen. So the old way to do it was to use a caret up and 2, which was squaring, and then you click enter, and it'll give you a number. Here we want to do 2 times p times q. So we want to use 2, and then we're going to use an asterisk or a star as the multiplication times p. You'll click on p and then times, and then you'll click on q, and then you'll click enter. And then lastly, we have q squared, which is going to be equals, similar to the p squared. We're going to click on the q value, and then you're going to caret and then a 2 because we're squaring. And just to double check, you're going to want to make sure that this all adds up to 1 because p squared plus 2pq, sorry, I'm just writing right now. Sorry. P squared plus 2pq plus q squared should equal 1. So we're going to want to add this and this and this, and that should equal 1. And it does, so perfect. And then you can kind of clear that just because, we like to double check our work, but you don't have to show evidence that you were kind of second guessing yourself. And now we're going to write our expected values, and the expected values are kind of easy because they just come from the tables up here. Or sorry, our expected values don't, that's my bad. Our observed values do. And so our expected values are based on this. Let's do our observed ones first though, because they're a little bit easy since they come straight from the table over here. And basically our observed is going to equal the sum that we pulled for however many AAs there are. So you click here and you would just click enter. Again, the reason why we're clicking it is because as you can see, just between those 2 values, that one went from 1 to a 2, just because when you click and enter, sometimes the randomization function will just recalculate. So you want to click them to keep the live flow working instead of kind of getting a little worried about what's happening each time the randomization function happens. Okay, so now we need to calculate our expected AA, AB, and BB genotypes. So we know that the p squared represents the AA, 2pq represents AB, and q squared represents BB. However, we do know that right now what we have over here are ratios or frequencies. But over here, we're working with individuals, okay? So that's the important part to note, that we're going to be working with individuals. And like I keep saying through all these videos, I pulled 17. So when you pull 16, you'll be multiplying by 16. The only reason why I'm multiplying by 17 is because I have 17 individuals, okay? So my rows from zygote all the way down here are 17 total, but yours should be 16 because I asked you to pull 16. Okay, so if I see in your work When I see your spreadsheet and I see you multiplying by 17, I will know that you were just copying me and that you were not using your brain at all. Okay, so please focus and make sure that you're actually using the number that you have here. When you do your large population one, you're going to be multiplying by 50, okay, not 16 and not 17, okay? So please keep that clear. So the reason why I keep saying multiplying is because in order to find the number of individuals in the expected, you're going to multiply your population size by the expected percentage of them. So you're going to be doing the percent times the population size, which we know is 17. And we're going to round because you can't have 0.97 of an individual in reality, because that's also kind of scary to think about. And over here, we're going to have this times 17, because again, that's our population size for my data. And then over here, we're going to have this times 17 one last time. And we're going to do some rounding just because these numbers are kind of iffy, but you always want to make sure afterwards when you round that there's a total that matches your total population size. So let me move this over real quick just because it is kind of in the way right now, and it's going to kind of get too crowded right there. So we want to round now. And we know that 0.97 rounds up to 1. We know that 6.2 rounds down to 6, and that 9.8 rounds up to 10. And you want to just double check always. I know it's kind of an easy thing to visually check, but you want to check that these all, oops, that's my bad, I referenced that incorrectly. So you want to check that what we have here is going to be a sum. Whoa. You can't use the keys here. So the sum is 17. So our population size of 17 is preserved, which is good. Because the rounding sometimes gets a little iffy, especially when you're in the 0.5s and 0.4s, where if you round too many numbers up, you might end up with a total that is higher than your population size, and then you have to adjust. So that's just something to pay attention to. I don't think it'll be a huge issue, but it is important to make sure that you are working with whole individuals, because we ain't got 9.8 people that we're working with. Okay, we have to have whole humans. If you remember the chi-square calculation, the chi-square formula is right here, and it's chi-squared equals observed minus expected, and then that is, as a numerator, is going to be squared and then divided by the expected. So we're going to need to do it multiple times. The easiest way is to do it over here with the 3 rows. So we're going to work on the 3 rows, and then we will just sum it over here in the box. So we have our expected and we have our observed over here. And so we're going to do our chi-squared for AA. So we're going to label it just because labeling is a good habit. And our chi-squared value for AA is going to be equal to, first off, we want to do 2 parentheses, and I'll explain in a second why. So we're going to be doing observed minus expected. So the observed is here, and we're going to minus the expected. You're going to close that parentheses because that is the initial function. And then you want to square it because that's part of the chi-squared function where you square the numerator. And then lastly, you're going to divide it by the expected. And then you'll click enter. Okay, and this changes each time you click enter. So the last time that you do your work, you're going to just take that value and run with that value in your explanation. So if you keep clicking enter though, it will keep changing. So now we're going to do our chi-squared of AB. And we're doing separately so that we can sum it together at the end, because that's an easy way to do it visually for you to understand what everything is doing. Okay, so we're going to do a similar setup where you have equals and you want to do 2 parentheses, and then you're going to do observed minus expected, and then you're going to square that, close your parentheses, and then divide it by the expected again. Enter. And the last one we want to do is our chi-squared for our BB population. And that's going to be based on observed minus expected, close the parentheses, square the numerator, and then divide by the expected again. Okay, so we did our chi-square separately, but remember, again, in the equation right here, this symbol represents sum. So we're going to actually sum all of them or add all of them together. And so our actual total chi-squared value is equal to the sum of all three of these, which is super easy to do in Excel. So our chi-squared value right now for mine in a population of 17, not 16, comparing the values of the parental generation in Hardy-Weinberg equilibrium, what they would have predicted, the expected, and the actual results of my population that was born, that we modeled, we have a chi-square value of 1.1. Now, we're comparing that 1.1 to a 5.99. And a 5.99 is much greater than a 1.1. So in my case, in my conclusion, I would have to write out basically word for word that I failed to reject my null hypothesis, or we failed to reject our null hypothesis at a degree of freedom of 2 and a p-value of 0.05, because our chi-square value of 1.1 is smaller or less than our critical value of 5.99. This means that we failed to reject that there is no significant difference between the number of individuals observed in the F1 generation of genotype AA, AB, and BB compared to the number of individuals predicted using the Hardy-Weinberg equilibrium equation, p squared plus 2pq plus q squared equals 1. You can literally restate your null hypothesis. And basically what that means is that our data doesn't show a big enough difference to show that it's not in Hardy-Weinberg equilibrium. Okay, because having no significant difference from the equation results and the equation predictions means that we're really, really, really close to Hardy-Weinberg equilibrium. And there's a little bit of variation, but that's okay because we're still close enough that there's basically no significant difference. If there was a significant difference, we would have gotten a value much higher than our critical value, and we would be rejecting our null hypothesis, which would be explaining that we are far away from Hardy-Weinberg equilibrium because of conditions, for example, having a small population. That would be my conclusion. All of that written down, okay? You will have your own conclusion based on your own numbers and your own results, and you will also do this whole thing for your large population. You can type out your chi-square, you can type out all of this work, you can handwrite it like I did, but you have to also show me the calculations that you did in your Excel spreadsheet or your Google spreadsheet. And that's easy to do with a screen cap as long as you're done with it. The last thing I want to make sure that you are paying attention to is that when you are explaining the conclusion, you are referencing the genotypes, the equation, and how the null hypothesis relates to the Hardy-Weinberg equilibrium. Because right now, the way that we have it stated means that if you fail to reject, you are in Hardy-Weinberg equilibrium. And if you do happen to be able to reject it, you want to explain it using one of the 5 conditions, or maybe more than just one of the 5 conditions, although you have to remember which ones we kept constant and which ones actually fall under that category. Hint, hint, it's probably population size related. Okay, that will be your chi-square analysis. You'll be doing 2 again, and you should be using a population size of 16 and a population size of 50. So this guided practice is going to run you through it, but you're going to be doing your own at the same time instead of just copying me word for word.